So the second speaker of the morning session is Andrey Pilipenko from Ukrainian Academy of Sciences. And today he will talk about flows, stochastic reflecting flows. Thank you, Andrey.
Thank you, Kilian. And at first, I would like to thank all organizers, Rus, Kavita, Alex, Kilian, for excellent conference. And I enjoyed talks very much. And there were a lot of discussions during talks, after talks, before talks. And the session with open problems were great. And I think that all of us have to thank Chris, who was a chairman, an excellent chairman there. Today, I will talk about stochastic flows. So what is stochastic flow? Assume that you have some random dynamical system. And if you start from the point X and you wait t units of time, then you get a point phi tx. And I start from all points. I fixed omega. I start from all x's. So I have a map. And I want to discuss properties of this map. For example, let me recall you the classical well-known properties. If dynamical system is not random, assume that A is just continuously differentiable function in Euclidean space, and assume the derivatives are bounded. And it's well known that, say, if you have this property, then immediately you have differentiability with respect to x parameters. And if you want to calculate derivative with respect to x, you have just to formally differentiate this equation. If you want to find equation for the second derivative, just formally differentiate twice and so on and so forth. If coefficient, if A is Lipschitz continuous, then, well, phi tx is continuous in both parameters and Lipschitz continuous in x. This map phi tx is homomorphism of Euclidean space. Indeed, you can solve the equation into other direction. Just take some x and solve this direction. Just write minus a, and you'll see that the corresponding is 1-to-1. Well, and another question is the following. Okay, assume that there is some mass, and phi t is a motion of particles. So you have some mass, for example, Gaussian distribution, and you push this mass and try to find the image measure, push forward measure. And it's well known that if mu is the absolutely continuous measure, then this push forward measure is also absolute continuous. And if the density of mu with respect to the Lebesgue measure is nice, say differentiable, positive, and if A is differentiable, then you have an expression. So it's some sort of Liouville type formula for the density of push forward measure. Well, and now let's consider, so I would like to do the same for stochastic, for equations with reflection. But at first, let's consider stochastic differential. Yes. A may be 0. If A is 0, then you have this. If A is 0, then phi tx is just x. Excuse me. No, yeah, there is a typo. This is d mu. I have to write d mu in the denominator. Yes, you're right. Thanks. Oops. And now let's consider SDE with nice coefficients. And nowadays, this theory is classic. And if you look at the result, you may say that, okay, they're approximately the same. They're approximately the same. Well, if coefficients are Lipschitz continuous, then phi t is continuous in Tx. And how to prove it? Well, you have some moment estimates, and it's very easy to write moment estimates and then apply Kolmogorov type theorem on continuity of a vector field. Well, and if they are smooth, then phi t is differentiable with respect to spatial parameter, but you have to write here -0, because when you apply Kolmogorov theorem, you lose a little bit. And well, if you wish to write down equation for the derivative, okay, this is the form. And if A and sigma are Lipschitz continuous, then phi is a homomorphism. But if you try to prove that this is homomorphism, you'll have a problem. This is a very non-trivial result. So when you study ODEs, you can just reverse the time. And you can do the same for stochastic differential equation. Okay, if you have equation in Stratanovich form, then you just write some minuses. But if you write equation in Stratanovich form, you have to make some correction. So you lose one derivative, and you lose one derivative. So if A and sigma are continuous say 2 times continuous differentiable, the proof is not difficult. Well, it's still not obvious, but if the Lipschitz continuous, this result is non-trivial. Okay, and if A and sigma k are Lipschitz continuous, it can be proved that phi is differentiable in the Sobolev sense, and actually derivative of equation for the derivative has this form. It's well known. So it's Rademacher's theorem that if a function is Lipschitz continuous, then it is differentiable in Fréchet sense almost everywhere with respect to Lebesgue measure. So these derivatives exist almost everywhere, and it can be proved that equation for the derivative has the same form for Sobolev derivative. And you have the result for push-forward measures if A and sigma are Lipschitz continuous. And now let's discuss SDEs. SDEs with reflection. Well, let me recall you the Skorokhod reflecting problem. So let us start with one-dimensional case and assume that you have a continuous function W. And we want to find a pair of continuous functions x and L such that x is non-negative and L grows only when x hits 0, and L is continuous and non-decreasing. And it was proved by Skorokhod that there is a unique solution to this problem. Well, moreover, it can be easily checked that there is a formula. And if we denote by gamma the Skorokhod map, so the map from the space C to the space C that moves W to X, we understand that this map is Lipschitz continuous. And what about SDEs with reflection? One-dimensional SDEs with reflection. Well, we assume that, that you have nice functions, A and sigma, say Lipschitz continuous, and we want to find a pair, phi and L, such that phi has the following representation. Phi is non-negative, L is continuous, adapted, and non-decreasing, and L grows only when phi hits 0. Okay, and it can be seen that to write this, phi satisfies these conditions if and only if phi t is equal to Skorokhod map of this. And then you just apply classical steps, Grunwald lemma, Picard iterations, and show that there is a unique solution, strong solution to this equation with reflection. Well, multidimensional case is more difficult because you have to talk about reflection and multidimensional Skorokhod problem. Okay, this may be a problem, and if you consider ortant or wedge or cusp, there are many possibilities how you can reflect, and many people studied. So if I forget someone, please excuse me. Okay, I didn't write myself. Well, and if the Skorokhod map is well defined, and if it is Lipschitz continuous, you can do the same procedure as in one-dimensional case. And I will not consider today bad situation where you have wedge or ortant. Well, my domain usually will be just half space with normal reflection, or maybe bounded domain with very smooth boundary, say C3, and this reflection vector field, I will assume that it is very smooth, such that I can make some local transformation of space and reduce my equation to this normal reflection. Okay, this is just formulation of SDEs, but I will consider only good cases, and in these cases you have existence and uniqueness. And now the first question: what about continuity in Tx? And it is not a problem to use the same approach as for classical SDEs in the whole Euclidean space. You can got some moments estimates, apply Kolmogorov continuity theorem, and prove that phi Tx, x is a starting point. This vector field has a continuous modification, and later on I will consider only this continuous modification. And well, let's consider okay, let me recall you properties of flows in the whole space. Homeomorphism, continuous differentiability, push forward measures are absolutely continuous if you start from absolutely continuous measure. So any of these properties is false for SDEs with reflection. And to understand what may happen, let's consider one-dimensional case, just reflected Brownian motion. Reflected Brownian motion in one-dimensional case. So the noise is the same. So before the hitting zero, all trajectories, so they move parallelly. And okay, nice properties, but it's okay, there are formulas. And it can be seen that you have monotonicity. So when, say, this green, so this green trajectory is always greater than or equal than this yellow trajectory. So when green hits zero, this yellow must be in zero. So what does it mean? That they meet together, and again, by uniqueness, they coalesce and then move together. So this flow is coalescing. And if you fix T and make a picture of phi T as a function of x, then you'll see the following picture. So this is x, this is y, y is phi T of x. So, and you see that okay, it is not a homeomorphism, it is not a diffeomorphism, yes, because for many starting points, they coalesce. And you see that there is one bad point where the flow is not differentiable. But okay, it's differentiable everywhere except of this, the only point. And well, let's try to consider multidimensional case and say consider a Brownian motion with reflection in say in a ball with normal reflection. And the first question is, we start from two different points. Is it possible that they meet together? And the answer is no. The answer is no. They don't meet together with probability 1, so they coalesce with probability 0. But please, these statements means that if x is not 0, then probability of this event is 0. But my question was another. So is it possible to move quanta inside? And you have to be very careful. Let me show you an example. So this is a plane. Let me give you an example of random web. Just take a line at random, say uniform distribution of this horizontal coordinate, and then you may consider this map. So if you take any two fixed points, then they meet together with probability 0. But some points after this map, they meet together with probability 1. And by the way, if you take some point and some small neighborhood and consider this mapping, this mapping is a local diffeomorphism, but the global mapping is not. So there is a difference. And let me explain you what happens and what is the result. And the result is the following. Well, assume that you consider a stochastic reflection flow in, say, in finite domains, smooth boundary, and result is this. Assume that you have a point, and assume that before time t, it didn't hit the boundary. Then this point do not coalesce with any other point with probability 1. Actually, this is clear because we know this property for stochastic flows without reflection. And if you don't hit these, then you have this property. Moreover, but this condition means the following. When this point hits the boundary, then with probability 1, there is a point that started somewhere from the boundary such that they hit the same position. And my reasoning was just topological and more or less obvious. Okay, let's consider the boundary and the motion of the boundary. So we have like homotopy. So this point was inside. And now when it hit this point, then it is outside of image of this. How can it be possible? How it is possible? Well, you cannot meet with image of this inside. So you have to meet some red point here. Okay, but well, there are rigorous topological statements, and so it's just for understanding. So what happens? What happens? So yes, we have coalescence. I explaining how it is possible. Yes, yes. So for each x here, when you hit the boundary, at this moment, with probability 1, there is some point y such that they have the same position. And well, for example, if you consider a Brownian motion just additive noise and assume that Brownian motion with reflection and assume that B at the point T is greater than 2 radiuses of the ball, then what does it mean? Then every point from inside hits this boundary. So all points will coalesce to some point. So there will be meetings. And the next result is a topological structure of the set phi t of D. So it has a boundary, it has inner part, well, which may be empty. And the boundary is the image of this, image of boundary of D. And all points that visited boundary before time t also are red. So they lie on the boundary of this set, And it's interesting to pose a question: is this boundary smooth or not? Is it smooth or not? Because, well, paths of a Brownian motion are not smooth, but the result is this. Hausdorff dimension of the boundary, Hausdorff is less than or equal than D minus 1, of D minus 1. And to prove this result, the idea of proving of this result about Hausdorff dimension and so on and so forth, it's a consequence of Sobolev differentiability of the flow on X parameters, on X parameter. So this is effect from Sobolev spaces theorem. And now let me explain you that you get Sobolev differentiability of phi tx in X parameters almost for free, even so, if A and sigma are Lipschitz continuous, then phi belongs to this space. Oops. And the proof is the following. Okay, at first, well, I don't want to consider Lipschitz coefficients, and I don't know how to work with reflection. So let me approximate my equation by equations with smooth coefficients, plus some penalization, some very strong penalization, but smooth in the neighborhood of reflecting hyperplane. Then you can prove convergence of phi n to phi in LP sense. So this is not my result. This method is well known. And it's known that if these coefficients are smooth, then phi nt is differentiable in X in usual sense. And then you write down equations for derivatives of phi n t in X are just linear SDEs, and you can control moments, and you see that, okay, when you have reflection or these additional terms that pushes you up, you have very nice estimates. And derivatives are bounded in LP. And LP is a reflexive Banach space. So the unit ball is, okay, let T be fixed. The unit ball is weakly compact. And now I use the fact that Sobolev derivative is a closed operator. Well, but and I use the following. It's like corollary of Banach-Sachs result, that if you have some sequence of elements of Banach space, and if it converges weakly to some function, so I selected subsequences, then there is a sequence of convex combinations that converges strongly. And now my Banach space is LP. So what do I know? I have phi nt. I know that phi n converges in LP to phi t, reflected process. And I know that derivatives are weakly relatively compact. Then I take linear combinations. And I know that functions convergent and linear combinations of functions convergent in LP, and linear combinations of the derivatives converge in LP to some process. But Sobolev derivative is closed operator, and this means that then phi is Sobolev differentiable with respect to x for almost all omega. Well, the question is how to write. I know existence of derivative, and the question is how to write equation for the derivative. And let me mention some papers on this topic. There are two difficulties. The first one is the following. If the boundary is not a plane, or if you have a wedge or orthant or oblique reflection, or if sigma is not constant, because if sigma is constant, and if you have additive noise, it's easier because your solution, for example, is Lipschitz continuous from the very beginning. But if sigma is non-linear, you have to work with stochastic integral, and it's very hard. It's very hard. And let me now explain you the intuition. Okay, I consider half plane, normal reflection. Before you hit this point, it's like usual SDE. You know how to write. You know how to write equation for the derivative. It's just linear SDE. So just differentiate formally and assume that you hit 0 at some instant t. Then vertical coordinate has a minimum. So what does it mean? Function has minimum. So vertical. So if the derivative exists, then derivative of vertical coordinate should be 0. And okay, so let's do the following procedure. Okay, you hit 0 sometimes. Well, the picture is not nice because, well, when you hit in the neighborhood of this point very, very many times. But assume that the picture is this: you hit, you reflect, and so on and so forth. So it's natural to expect the following. Well, at first you solve linear stochastic differential equation. Then you hit. Then you say, well, vertical coordinate, derivative of vertical coordinate should be 0. So multiply it by projector to all other directions except of, so P is the projector to all horizontal directions. And okay, if you are not in 0, just follow the linear stochastic equations and so on and so forth. Well, as I said, okay, and in my first paper, okay, so this is a procedure. This is a procedure. So you cannot say, okay, wait before and multiply. There are countable number of excursions, and the moment when you exit from the point is not stopping time. But the result is this. The SDE has the following form. So let's consider the following random map. So you have a stochastic process, say Cadillac stochastic process. P is projector on the horizontal directions. And if you have a function phi, if t is a time, you take the last visit to 0 before t, and this operator p makes this f of t minus projector of f to the horizontal lines, and equation for the derivative has this linear form with some random operator. So it is not difficult to show that this equation has a unique solution, but there are a lot of work to show that this is equation actually for derivative. And if you consider reflecting Brownian motion in a domain with normal reflection, you may suggest that equation for the derivative has the following form. Okay, assume that pi x is projection to the tangent space. Okay, this is trajectory. You have some heatings. Let's consider just product of this orthoprojection operators. P at this point times this point, this point, and this point. Actually, this is wrong answer. And Chris considered this problem, and there were some corrections. There were some corrections related to the curvature of the shape of this domain. So you have to project and to multiply by some correction map that is related to so-called Weingarten operator. Okay, and what about push forward measure? And well, let me recall you the picture. My picture, okay. So these green points, they did not hit boundary before times t. So if you take image of this green with respect to this map phi t, then push forward is absolute continuous, because okay, you don't have reflection. You can make a reference to classical results. Well, not classical, but known results for stochastic flow without reflection. And you know that all these red areas, so points that hit boundary before times t, are here. And the dimension of this set is d minus 1, or maybe less, or maybe less. And the question is it true? Is it true that push forward of that this measure, this push forward measure, is absolutely continuous with respect to d minus 1 dimensional Hausdorff measure? Well, this is very abstract question. Hausdorff measure of dimension d minus 1 or Sobolev differentiable function, but let me recall you one result from geometric properties from geometric measure theory. Assume that D is a set of RD, measurable set, and assume that F is differentiable at X, at D. In any sense, like Frechet or Gateau or Sobolev or some derivative, directional derivatives, approximative derivatives. And this set D may be terrible. It maybe nowhere dense set of positive measure. Then the statement then, okay, assume that then for any epsilon greater than 0, there exists a function f epsilon that is continuously differentiable everywhere, such that Lebesgue measure of x's from D, where f of x is not f epsilon of x, is less than epsilon. So if you have some type of differentiability at D, then there is nice, really nice, continuously differentiable function, okay, such that f is equal to f epsilon. So think about Sobolev Sobolev derivative, like about usual derivative, and the result is, okay, this is just general result that if rank of the derivative is greater than or equal to d minus 1 for every x, then you have absolute continuity. And there are some sufficient conditions. For example, if you have Brownian motion in a ball, then this is the case with normal reflection. This is the case. And the last question that I want to discuss with you is flows in a wedge. And okay, let me start from the very beginning. So I wanted to construct strong solution of the SDE for Brownian motion with oblique reflection in a wedge. Of course, the vertex is a very bad point. So we understand that if something wrong happens, that it must be at vertex. So I decided, okay, I have to start. Well, maybe the case when the flow hit the vertex is probability 1 is not is very difficult. So I decided to study another case when you never hit the vertex, and I wanted to just start from the vertex and prove the result. Well, of course, I was aware about Vardan's and Williams' paper, and my plan was as follows. Okay, if you start not from this, then okay, small neighborhood also, don't visit this, and I can do this for any point with rational coordinates, and I hope that I can construct a flow for any for these starting points, and I hoped that okay, the flow does not hit 0. Okay, every ball don't hit 0, and actually I have continuity in x and t, and then I wanted to send this point to 0 and got sequence of continuous mapping, and then try to pass to a limit. And okay, there is a classical Yamada-Watanabe theory that states that if you have weak existence plus uniqueness, then you have strong existence. But sometimes if you have weak uniqueness plus strong existence, then you have strong uniqueness. So I wanted to construct by this procedure a strong solution, and then say, well, we know weak uniqueness, so we have a strong solution. Well, and after yesterday talk by Chris, I was not able to sleep. Life is terrible, and no, not life, but the world is terrible. We don't have strong uniqueness. Well, in some sense. Well, this are plausible reasoning. Because we take points with rational centers, but who knows? Maybe there are other points. There are other points. Maybe it is impossible to construct a flow that does not hit zero and continues. Yeah, and the first question is, okay, is it true that this flow hits zero? Assume that reflections are here outside of this point. The first question: is it true that there is x such that x may be random, such that you hit zero? Okay, let's consider simpler question. Assume that you have some angle, and the question: is it possible that there is a point such that you hit vertex without hitting this rays? Well, the first thought is, okay, if you have two-dimensional Brownian motion, and if you take fixed time t, you know that if you fix t, then immediately you rotate very many times around this point. And if you go back, okay, you observe again Brownian motion. So probably it is impossible, but well, I take fixed t, but not any t. I can do this only for rational. And okay, so I believe that this is impossible. So what do you do? But when you cannot prove, you pray to God and say, okay, what happened? Is there continuous flow? And I got the answer, and the answer was, okay, you are a sinner, and but not so bad. Okay, I will help you. And the Lord was kind and clever, and he told me, okay, I give you permission to believe in Euclid fifth postulate and axiom of choice. So go and follow the rules, follow the axioms, and follow the Brownian path. Okay, I say thank you. I believe in axiom of choice and in fixed postulate. So, and I tried to follow the Brownian path, and I decided to do as follows. I cannot start from all points. Okay, so I took just, I decided, well, let's consider the simplest case. Let's start from this domain. And what are the images? Before you hit this or this, you'll see the same angle. And assume that reflections are normal. Reflections are normal. So if you fix a point, you never reach zero. Okay, so now what happens if you hit, for example, this side? And it can be calculated explicitly. So you have this set and you hit, then you see that the picture, it looks like this. The same picture. The image of this is the same angle. But okay, again, so but the vertex, you see, the vertex will be different. And if you write down SDE for the vertex, you will see that vertex satisfies SDE, but with these reflections, this reflection and this reflection. So what does it mean? This means that the vertex of so I have floating these wedges, and they will hit zero. And actually, these green points, never hit the boundary. So when you hit, then you glue to this red line, and you move this wedge inside wedge, and all the times you'll have points here. And this is the argument that with probability 1, you'll reach zero without hitting these boundaries if this angle is greater than pi/2. So I didn't believe in this result. So I asked many people, so is it correct? Because it's unbelievable. And later on, I discovered that this result was proved even, okay, even in multidimensional case, by another method by Chris and Shimura. So Shimura proved result in two-dimensional case, and Chris considered multidimensional space. And it was not a paper about hitting zero. It was a property of multidimensional Brownian path. Is there a random point such that trajectory is inside the wedge or a cone? And there were some conditions. And conic points exist, and pi over 2 is just critical level. And the result is the following. So the flow hits the vertex with probability 1 if and only one, if and only if one of the following conditions is satisfied. Vardan-Williams condition, or xi greater than pi over 2, or some another condition. Okay, that's all for today. Thank you for your attention.
Thank you very much. Do you have any questions, comments?
Okay, so your last theorem states 3 different conditions, and any one of them. So if and only if one of them is satisfied. So I guess the picture that is on the blackboard, right, refers to the first one. Which one is this?
Second. The
second one.
Yes.
So can you briefly just say something about the first and the third?
The first condition is Vardan and Williams. Then condition. The first means that every point hits with probability 1. This one means that you can hit without touching, even without touching the vertex. And the short one is something in between. And the proof was, well, when you consider these pictures, well, sometimes you have this, the image is wedge, sometimes not, it's more difficult, but you have the minimal point, and the minimal point satisfies certain SDE, and this is condition for minimal point. So SDE with reflection.
And if any of this strict inequality becomes large, I mean, inequality, sorry, it's no longer true.
Oh, if and only if and only if.
But I mean, can you quantify still this probability in some?
It's 1 or 0. It is 0 or 1.
So could you explain again what is your result regarding the measure of the boundary of the points that by time t have not hit the boundary? What is exactly the statement of the result regarding the boundary?
The result is this. You have reflected diffusions with nice coefficients, and you consider, you start from every point, and assume that this set is phi t of d. For example, so it may be smaller than d. It may be smaller than d. Then it has boundary and inner part.
Sure.
Inner part are points that didn't hit without reflection before time t. And this is image of this,
sure.
Image of this. And the statement is dimension of this boundary is d minus 1.
Yeah, but you had also a result regarding the measure of that.
A measure. And now you take, say, Lebesgue measure, and then you push.
Sure.
Then you push, and many points come to this boundary.
Sure.
And the statement is, this push forward measure is absolutely continuous with respect to Hausdorff measure, dimension d minus 1. So it's like surface measure. It's like really surface measure, d minus 1 surface
Okay.
measure. So think that, okay, I have Sobolev differentiable, but for any epsilon, it's like image if the map is continuously differentiable. So it's almost image of smooth manifold by smooth map. Well, there are some restrictions. For example, it should not be like perpendicular segments on this boundary. So if you have a circle, then that's okay. Because if you have a circle, a ball, you cannot collapse to a sin. But if you have two perpendicular segments, then yes, you hit this. You hit. It's possible that later or earlier you will collapse to a single point. No. There was a condition. Yeah. There were some conditions. And they are satisfied if this is not the case. So not for all domains, but domains that are non-degenerate in this sense.
Yeah. Thanks, Aaron. Just to continue. So here is normal reflection for all these
Here,
results?
normal
reflection. And you have some expression for the density, I guess, also on with respect to the surface house measure. No.
Well, there are no nice formulas for. It's like you have to look at the inverse image and some and disintegrate somehow, but no beautiful expressions.
And if you change normal reflection, then this condition on this flat bits would be different.
Well, this is a question. Theoretically, you may apply Ito formula to make, if you have not so terrible smooth reflection, you can make normal, and you do for normal and return back. But I don't have nice formulas like Chris formulas with this shape operator on the boundary when the boundary is not flat. Yeah, I wish to do this, but well, I tried and I saw like it is possible, but calculations were very terrible and not beautiful, so I stopped to do it.
Follow the Brownian path. Any last questions? Okay, so let's thank Andrey again.